In this video, we're looking at an example of optimization. The problem is an offshore oil well needs to transfer its crude oil to a refinery that is 8 miles down the shoreline. The well is 5 miles from the shore. The cost of laying pipe is $1 million per mile underwater and $500,000 per mile on land. Where should the pipeline be laid to minimize the cost of laying the pipe? Okay, and you should pause the video and read the question yourself as many times as you need to in order to understand what we're asking for. A good idea, almost always, for working with problems like these is to draw some kind of a useful diagram to help organize the facts. So that's exactly what I'm going to do now. Let's try to draw in a diagram here. So we have this offshore oil well. So we need to draw in a shoreline. Here's my shoreline. And then the oil well is out at sea. It's out here. I'm going to put this dot. This is my dot that represents this offline oil well. Okay, there's my oil well. And we actually are told in the problem that this oil well is 5 miles away from the shore. If you need to, pause the video, read the problem to find where it tells us that the distance from the oil well to the shoreline is 5 miles. So here, this distance is 5 miles. Okay, it also says that there is this refinery, which is a refinery is a sort of a factory where you take crude oil that came out of the earth and you turn it into useful oil. And that refinery is 8 miles down the shoreline. So from here until we get to over here, 8 miles from there to here, let's say. Okay, and then right here we will build our refinery. I'm not sure exactly what a refinery looks like. It's probably a factory that has a lot of smokestacks. How's that for artwork? Okay, so the refinery over here, maybe I'll label this is where the refinery is. The refinery is 8 miles down the coast, the shoreline. The oil well is out here at sea. It's out in the ocean someplace, 5 miles out into the ocean. And we're trying to find a way to deliver the oil from this well to the refinery in the least expensive way. That is to minimize the cost. Okay, great. And then we were given some useful information about the cost of laying down pipe on land and laying down pipe at sea. Okay, very good. So, and we want to ultimately see where should we put this pipe. Okay, I'm going to change colors here to sort of draw in some a possible path for the pipe. So let's see. I'm going to maybe make the pipe. I'll make the pipe red. Okay, so I'm switching colors, I think. We have to start, I'm going to start here from the refinery, and we'll build pipe from the refinery going along the shore for a certain distance, maybe. Maybe from here over. From here over, we're drawing this pipe. I actually would like to make it as straight as possible, but okay, and at some point, since I don't think would go along, although it's possible, I don't think we would go along the shore all the way and then go out to sea. At some point we want to go ahead and start building that pipe underwater so we can go straight to the well. So there's actually these two different parts of the pipe. There's the part that's underwater, and there's the part that is on the ground. And it tells us actually that it costs a different amount to do those. So the cost of laying pipe is $1 million when you're underwater, and it's $500,000 per mile when you're on land, and it's going to be important to keep track of that. Before we can really use the two different costs, we have to know the distances that we're talking about. So we have to try to improve our understanding of this a little bit. I will write down something that it might be kind of good to keep track of. This, go back to blue. Okay, what we're really working with here is we're trying to minimize the cost. So it would be nice to have an equation for the cost. Well, see, the total cost, the cost of laying all the pipe, is going to be equal to the cost of the pipe per mile underwater times the distance underwater and then plus, right, the other cost. The other cost is the other cost that we're dealing with here is the cost of laying the pipe per mile on ground. Over the ground times the distance on the ground, right? And I suggest, if you're having a hard time setting up these problems, which is probably the most challenging part of doing these problems, it's not a bad idea to work out. See how I wrote down what is the cost using really just words? I'm just trying to find the relationship between all the parts before I even start substituting anything in. So the cost of the pipe per mile over ground times the distance over the ground, right? The distance over ground. I think you can read this and you can understand that must be true. That is what it's saying. And now the challenge of it is to come up with symbols or equations. We need either a symbol, a number, or an equation. Okay, we need a symbol, a number, or an equation for this part. A symbol, a number, or an equation for this part. A symbol, a number, or an equation for this part. And a symbol, a number, or an equation for that part, so we can put it all together and have a chance at solving the problem, right? Okay, well, let's introduce some symbols. Let's put some symbols into I'm going to put some symbols into the diagram here. Maybe I'll call this distance over the ground. I'll call that G. G stands for the distance over the ground. And I guess if we're really doing this right, we should say that someplace. G represents the distance over ground. Yeah? And let's call the distance here from the oil well to this pipe, this part of the pipeline that's underwater, I'll call that W. W represents the distance under water. Yes? Yeah, not bad. As a matter of fact, in a way, with those two symbols, we can improve upon what we've only done in words. Down here, I can improve upon this. I know the cost of the pipe per mile underwater, right? I underlined those in the problem, yeah? The cost of running the pipe per mile underwater. And in order to make some of the math easier, I'm going to switch from using units of dollars to using units of $100,000. Okay, so see, $1 million is the same as $100,000, right? So what I'm going to do is I'm going to switch to I'm switching my units here. Instead of dollars, I'll put that over here someplace. Let's see if I can find where the pen is. Yeah, it looks like the pen is... Okay. Alright. So I'm going to switch from, instead of dollars, my units. I'm just discussing the unit. Instead of my units, instead of using dollars, I'm going to instead use $100,000. You see, that just makes the numbers smaller. So for example, if you have $1 million, that is the same as having $100,000. And if you have $500,000, that means you have $500,000. I think you understand. See, it's just going to be nicer to use numbers like 10 and 5 in my math instead of using numbers like 1,000,000 and 500,000. Okay, so the cost of pipe per mile underwater is, well, that was $1 million, which is $100,000, times the distance underwater. We have a symbol for that now. The distance underwater is W, plus the cost of pipe per mile over ground, right? Which turns out to be $500,000, which in units of $100,000 is just 5, times the distance over the ground, which we have a symbol now for that. That is G. Okay, well, this is, a little bit better than before, I think. It's looking a little bit more mathematical, at least. So right now I have the cost is equal to 10W plus 5G. It's a pretty good to know that that is the relationship that we're working with. What we need to do now is we need to write, we need to figure out a way of writing both W and G in terms of some common variable, right? Because we would like the cost to be a function of one single variable. Okay, so let's do that. I'm going to go back to the diagram to figure out, well, what exactly is this W? See if we can use the rest of the information in the problem. Okay, so here we are. W. How can we write out what W is? And somehow I suppose we need to be using that this is 5 miles, or possibly that this is 8 miles. Well, one thing that I notice in my diagram here is standing out to me is that my diagram has a right triangle in it. And whenever I make diagrams that have right triangles in them, right away I start thinking, is it possible that I could use the Pythagorean theorem? Yeah? Okay, so let's see if we can write out. In order to use the Pythagorean theorem, I know this leg of the right triangle. I don't know this one yet, but I know that the whole thing here is 8 miles, right? So what if I just I'm just going to now just call this, since I don't know what it is, I'm just going to call this x. So x is the distance from where we stop. X is the distance from where we stop laying the pipe on the ground to where the oil well is, if we were to go straight from the oil well to the shore. So x is the distance from there to there. Okay? Well, now I have enough symbols that I can sort of rewrite W in terms of x. So using the Pythagorean theorem, W squared is equal to 5 squared plus x squared, right? And what that means is that W is equal to the square root of 25 plus x squared. So that's pretty good. Alright, so now I have a way of, I don't need to use this W anymore. I can now use x, but if I'm going to use x instead, I better figure out what is G in terms of x. Well, that's not so bad, because over here, what is g? Well, see, the entire distance would be 8. The entire distance would be 8. But then we're coming back x, so the way to think about that is that g is going to be that entire distance at 8 miles. But then we come back x, so that's minus x. So g equals 8 minus x. And this is very, very good now, because now I know what w is, and I know what g is in terms of x. Okay, the big idea here is that at some point when you're doing these problems, you need to write all of your symbols in terms of a common symbol, and in this case I'm using x. Okay, in fact, now I can rewrite what is the cost. Okay, I'm going to rewrite what is the cost using those ideas. Okay, so we have here now the cost is 10 times w, but what is w in terms of x? Oh, w in terms of x is the square root of 25 plus x squared. Okay, that's w. And now it's plus 5 times g. Oh, but g is 8 minus x. Okay, and this is fantastic, because now I have, see, I've gone from writing it all out in words, which shows the relationship between all the important parts. I chose some symbols to stand for some of those parts so that I could get going, right? And then I rewrote all of those symbols in terms of a common variable. In this case, it's x. And at this point, I actually have a function. See, this is an equation, but it's really also a function, because this is giving me the cost as a function of x. C of x equals 10 times the square root of 25 plus x squared plus 5 times 8 minus x. So that's very good. And this is going to be a function now that we can use, we can apply calculus to actually answer the question that was originally asked. So before I start taking derivatives, I think I'll just simplify this a little bit. This is 10, I'll write this as 10 times the quantity 25 plus x squared to the 1/2. And over here this is, I'll distribute the 5 to get 40 minus 5x. So this version is probably nicer for just giving someone the function, but this version is probably a little bit better for when we start taking derivatives. Okay, very good. Let's go ahead now and find the derivative of this, right? So we want to find the derivative. Let's find c prime. Okay, so c prime of x is equal to, it's going to be a 10 here, times, this is the power rule along with the chain rule, so bring down the 1/2. Yeah, just write down what was inside there, 25 plus x squared to the negative 1/2 power. The negative 1/2 comes from 1/2 minus 1. Now we have to use the chain rule, so it's going to be times, the derivative of 25 plus x squared is 2x, right? Okay, that takes care of that part, plus the derivative of 40 is 0, so I don't have to worry about that. The derivative of negative 5x is negative 5, so it's plus negative 5. This actually is the derivative. It can be cleaned up a little bit. Okay, so let's see. I have here 10 times 1/2, which would be 5. And then 5 times this 2 gives me 10 again. Another way to look at it is this 1/2 times this 2 cancel each other out, and I get the 10. So this is still 10. It's actually 10 over, if I take care of this negative 1/2, it's 10 over the quantity 25 plus x squared raised to the 1/2 power. Oh, and then this x is up in the numerator, so it's 10x over the quantity 25 plus x squared to the 1/2 power. And then just minus 5. That is what the derivative is, and it's not such a bad form. But think about the things we would like to do with this derivative. We'd like to find its critical numbers so we can find where the maximums and minimums are. So in order to find the critical numbers, it'll be better to keep simplifying a little bit, try to get a common denominator. So this is the same as 10x over the quantity 25 plus x squared to the 1/2 power minus, here's my 5, but I'm going to create a common denominator now. So I'm going to multiply this 5 by the quantity 25 plus x squared to the 1/2 power over the quantity 25 plus x squared to the 1/2 power. This is just to get a common denominator, which lets us rewrite this as, this means now that we have 10x minus 5 times the quantity 25 plus x squared to the 1/2 power over the quantity 25 plus x squared to the 1/2 power. Alright, this is what the derivative is in probably the most useful form. Okay, so we have now found the derivative. What do we do with the derivative? How do we use the derivative? If you've been one of the most useful things you can do with the derivative is you can use it to find where does the original function have relative max, relative minimums. And the way you do that is we have to first find its critical numbers. There will be some critical numbers. No, the denominator won't give us any critical numbers. Really, the only place that this function is going to become equal to 0, it depends upon its numerator, right? So in general, when you have a fraction that's equal to 0, really you need to find where will a equal 0, because it's only the numerator that will ever make a fraction become equal to 0, or a rational expression. Okay, so let's set the numerator equal to 0 and try to solve for x. So this is now 10x. What we're doing here is we're trying to find critical numbers. Okay, and we're setting the numerator equal to 0. So 10x minus 5 times the quantity 25 plus x squared to the 1/2 power is equal to 0. Before I go on too far, I just want to say you can get critical numbers when the denominator becomes equal to 0, because that would make it undefined. But this denominator will not be equal to 0 for any of the values of x that we are interested in. So, and you should take a look at it and decide what the reason for that is. As a matter of fact, this denominator can never become equal to 0, because x squared will always be positive, which means I'll be adding 25 plus a positive number, and when you take the square root of the positive number, it won't become 0, and it won't become undefined either. Okay. Alright, so let's keep on going. So 10x minus 5 times the quantity 25 plus x squared to the 1/2 power equals 0. I'm going to subtract 10x from both sides. So now I have negative 5 times the quantity 25 plus x squared to the 1/2 power equals negative 10x. How about if we multiply both sides by negative 1? So you multiply negative 5 by negative 1 and you get 5 times the quantity 25 plus x squared to the 1/2 power. When you multiply the right hand side by negative 1, you get 10x. Okay, so far so good. I'm going to now divide both sides by 5, because I'm trying to isolate this quantity to the 1/2 power. Divide both sides by 5. So now I have the quantity 25 plus x squared to the 1/2 power is equal to 2x. So far so good. Now's the time to get rid of this 1/2 power. Let's do that by squaring both sides. So see how I'm squaring the both sides of this. Whatever is due to one side is due to the other. So 1/2 times 2 becomes 1, and now we have the quantity 25 plus x squared equals, now when you have 2x and you square it, it's like 2 squared and x squared. So 2 squared is 4 and x squared is x squared. So this is what we have now. Okay. What else can we do here? Alright, these parentheses are there to help you see what's going on. They're not really serving any purpose anymore, so I'll get rid of them. 25x squared equals 4x squared. How about if I subtract x squared from both sides now? Minus x squared, minus x squared. Now I have 25 equals 3x squared, right? Some people prefer to have the x's on the left, so I'll rewrite this as 3x squared equals 25. That's the exact same thing. Now we'll divide both sides by 3, and we get x squared equals 25 over 3, which means that I can now take the square root of both sides. So the square root of x squared has to equal the square root of 25 over 3. Yeah. The square root of x squared is x, and over here, this is really a plus or a minus if we're being really careful about things. So this becomes the square root of 25 over the square root of 3. The square root of 25 is 5, so this is plus or minus 5 over the square root of 3. I don't really need that negative because this x represents a distance. So really we have x equals the square root equals 5 over the square root of 3. This is a critical number for the this is our critical number for the derivative of the cost. Okay, this was the derivative of c of x that we just found, and this is one of its critical numbers. It seems to be the only critical number. Okay, well, what are we going to do with this? One option could be to make a sign chart and try to go from there. I'm going to do something that's a little more powerful even than that, which is I'm going to remind you of the extreme value theorem. The extreme value theorem says that a continuous function on a closed interval closed intervals look like this. An endpoint A that you include and an endpoint B that you include will always have an absolute, this is a big deal, it's an absolute max and absolute minimum on the interval. Okay, so in other words, as long as we stick between A and B, including both A and B, those are x values. Okay, as long as we stay between A and B, including both A and B, and as long as the function is continuous, the function will have an absolute maximum value and an absolute minimum value. This is important and useful, and it's important and useful for this problem also because maybe we can find a closed interval like that and use that to our advantage. And to work that out, I want to go back to the diagram a little bit. We're thinking about, can we find a closed interval like that? Well, we're thinking about x values here. So let's think about the absolute smallest that x could possibly be. The absolute smallest that x could possibly be, or the smallest, I shouldn't be using the word absolute there, because usually absolute maximum and minimum refers to values in the range of the function, and here I am talking about values of x. But the smallest that x could be, the smallest that x could be is really 0. See, if x is 0, that means we lay the pipe on the ground, we would lay it 8 miles, and then turn 90 degrees and head out to sea and lay some more pipe. But x could possibly be 0. So you see, x is something that belongs to this interval. It belongs to the interval between 0, being the smallest. And what is the biggest that x could possibly be? Well, you could have x going all the way over to the refinery, in which case the x would be an 8. And so right here we have created a closed interval for this function. And whenever you can create a closed interval for your problem, which becomes sort of the closed interval that you're concerned about with your function, then you can use the extreme value theorem, which tells you about the fact that it has to have absolute maximums and absolute minimums. So I'm going back here. There's our extreme value theorem. We have this closed interval. See, we know that x, we're talking about this cost function that we found earlier, but it's a cost function on the closed interval. (0 to 8), because of what we were talking about earlier. So the way we can find this absolute maximum and minimum is it works like this. We have to see here, A is called an endpoint, and B is also called an endpoint. And over here we found these critical numbers, right? So we have endpoints and critical numbers. And the way the extreme value theorem works is you just have to evaluate your function at the endpoint. So there'll be the first endpoint. There can only be 2 endpoints. And figure out what it is. Then evaluate the function at the first critical number and see what that is. This is the critical number that's between the endpoints. There's no reason to evaluate a critical number that is not between the endpoints. I hope that makes sense. Evaluate it at the second critical number that's between the endpoints. Okay, see what that comes out to be. And you keep doing that until you run out of critical numbers. This is the nth critical number that's between the endpoints. Until you run out of critical numbers that are between the endpoints. Yeah? And then you check you find what is you evaluate the function at the second endpoint. Okay? Alright, and whichever of those is the biggest value is the absolute maximum, and whichever of those is the smallest value is the absolute minimum. That's the idea of it. Now let's actually do it for this problem. Okay, so here is our cost function, and let's evaluate that at the first endpoint. So, rather than having to scroll up for you, I'm going to write down the cost function that we came up with earlier. The cost function that we came up with was 10 times the square root of 25 plus x squared, and then to that we have to add 5 times the quantity 8 minus x. This is the original function. Okay, we found its derivative in order to get the critical numbers. We thought about what is the closed interval for this problem, and we found that is from 0 to 8, and now we're going to use the extreme value theorem to find the absolute maximum and the absolute minimum. So first, I evaluate this function at the first endpoint. This is the first endpoint, 0. So C of 0 is 10 times the square root of 25 plus 0 squared plus 5 times 8 minus 0. And then that simplifies to 10 times the square root of 25 plus 5 times 8, which is 10 times 5 plus 40, which is 50 plus 40, which is 90. Keep in mind the units. This is in units of $100,000. So this is $90,000. $90,000 is the same thing as $9 million. Okay, so that's a C of 0. In other words, when x is 0, the cost would be $9 million. Now we have to evaluate the function at any critical numbers that are between the endpoints. So are there any critical numbers that are between 0 and 8? Okay, a critical number between 0 and 8. Yes. The 5 over the square root of 3 is between 0 and 8. Okay, so I'm going to evaluate the function there. So I have to find what is C of 5 over the square root of 3. And when I do that, that becomes 10 times the square root of 25 plus 5 over the square root of 3 squared plus 5 times 8 minus 5 over the square root of 3. Okay? And this is really just a matter of plugging that into the calculator. When you plug that into the calculator, you will get a value out. Looks like, so I'm plugging it into the calculator here. When you plug that into the calculator, you'll get a value out of, this is equal to, or approximately equal to, $83,300,000. $83,300,000 is about $8.33 million. Okay? So if at that value of x, the cost is $8.33 million. And finally, we now need to, if there were any other critical numbers, we would keep going, but there are no other critical numbers between 0 and 8. So now I'll do the last endpoint, C of 8. Okay? What you're going to go ahead and plug it in. I'll write it down. I'll write it down just so that no one gets... So this is the 10 times the square root of 25 plus 8 squared plus 5 times the quantity 8 minus 8. Yeah, so this 8 minus 8 will simply go away. And we will end up with, when you plug that in, you put it into your calculator, the number that comes out will be 94.34. This is in units of $100,000, which is the same as $9.43 million. Okay, so there we have done it. See, we found the value at the endpoints. This is C evaluated at the endpoints. And also we found the cost evaluated at any of the critical numbers in between. Okay? And now we look and see which of those was the biggest, which of those was the smallest. So, okay, if x is 0, the cost will be 9 million. If x is 5 over the square root of 3, the cost will be 8.3 million. So I'm focusing on the millions here. This one, and this one. Okay, so 9 million versus 8.33 million versus 9.43 million. This is clearly the absolute minimum value on the interval from 0 to 8. On the other hand, and it didn't ask us for this, but interesting to note that this is the absolute maximum value on the closed interval from 0 to 8. Yes. So if you wanted to try to lay the pipe so that you would have to pay as much as possible, you would want x to be equal to 8, which would be a silly thing to do. Most people want to minimize their costs. So the most rational and intelligent choice is to set x. Let's let x equal 5 over the square root of 3. This is in units of miles. Okay. When x is 5 over the square root of 3, that minimizes our costs. Okay, minimizes our cost of laying pipe. I want to make sure that I'm answering the question that they're asking. I think this is a pretty good answer, but I do want to make sure that we're answering the question that they're asking, and which may take just a little adjustment. So I'm going back to the problem and my diagram. Okay, here's the problem and the diagram again, and it is asking where should the pipe be laid to minimize the cost of laying the pipe. I just want to remind you what, we solved it in terms of this x, and what is the x? Well, the x is not really the distance from the refinery, it's really the distance sort of after the refinery. After it's how far do you have to keep going to the left after you've stopped laying pipe on the ground, right? So we need, I think it would be nice to express the answer in terms of g, in order so we can say how far should we lay the pipe from the refinery along the ground, right? So if I want to express the answer in terms of g, I just have to remember how g relates to x, right? So that's just 8 minus x. So when I do that, I go back now to write down my final answer, right? Just going back here, looking at all that good math. Okay, look, going back, this is the value of x that minimizes the pipe. Now remember, the distance along the ground, g, was equal to 8 minus x, so this is 8 minus 5 over the square root of 3. This is in units of miles. And when you type that in the calculator, you can write that as 5.11 miles. So a nice way to write the final answer is that we can say that we minimize the cost of laying pipe by putting the pipe on the ground for 5.11 miles, right, before turning and then running it under C, right? So 5.11 miles from the refinery is probably a pretty good answer, right? So we have here 5.11 miles from the refinery. That's the once you move 5.1 miles from the refinery, that's where you turn and start putting the pipe under C.